Welcome back from spring break. I hope everybody had a wonderful and relaxing week off. Today we're going to be starting chapter 8, which is going to be more of application of many of those trig functions that we have learned about in the past couple of chapters. So this first one, we're going to be solving a triangle. Now what this means is that we're simply going to find all of the missing angles and sides in the triangle. Our particular triangle is going to be, or the first triangle that we're going to look at here today is going to be a right triangle. So right away they're telling us that angle A is 90 degrees. Now, one thing I do want to point out, when we are labeling a triangle, we use capital letters for angles and we use lowercase letters for sides. Also, the angle and the side that are across from each other in a diagram should always have matching letters. So for example, if angle A is my 90-degree angle, then the side across from it, side A, is going to be my 29 in whatever units. It doesn't give us units here. Now, the other two angles in my triangle are B and C. It doesn't matter which is which. However, side B is 21, and that has to be across from angle B, so I'm going to call this one 21. And then the remaining side, we're going to call that side C, since that's unknown at the moment. So our task here, I'm going to erase some of these interior angle or arrows, excuse me. Our task is to find the measure of angle B, the measure of angle C, and side C. Now, because it's a right triangle and we're looking for, and we know two of the sides already, we can find the missing side by just using Pythagorean theorem. In Pythagorean theorem, we're going to take our legs squared plus our other legs squared to equal the hypotenuse squared. That means we'll do 21 squared plus c squared equals 29 squared. And if we do a little bit, let's see, 29 squared minus 21 squared, c squared will equal 400, and if I take the square root of that, c is 20. This happens to be one of the less commonly known Pythagorean triples, but it is a Pythagorean triple. So once we've gotten this first side, c being 20, now we can move on to our angles. With our angles, we're going to have to resort to those trig ratios. So pick an angle that you want to solve for first. I'm going to say let's go for angle B. I always recommend circling that angle in your diagram. Then I would recommend picking the two sides that you were given rather than using the side that we just found, just in case there was any mistakes made or if we had, for example, a rounded decimal. So I'm going to use this side and this one. In relation to angle B, this side here is opposite and this side is the hypotenuse. So in terms of our trig functions, we call SOHCAHTOA, going way back to the introduction to trig as well as our geometry. The one ratio that compares opposite and hypotenuse is going to be the sine function. So to find angle B, we're going to write a trig function for the sine of angle B equals the opposite 21 over the hypotenuse 29. Remember that whenever you're solving for an angle itself, you're going to be using the inverse of sine. So we'll do the inverse sine of 21 over 29. And if we put that in our calculator, we're going to get approximately 46.4 degrees, but we'll just do a quick double check of that. Sorry. Double check that your mode is on degrees. We're going to do the inverse sine of 21 over 29, and we've got about 46.4 degrees. Now keep in mind that once we have found angle B, 46.4 degrees, we know that in any triangle, in any right triangle, the two acute angles are always going to add up to 90 degrees. So if I want to find angle C, I can subtract 90 minus my previous answer, and I'll get about 43.6 degrees. So that is solving a triangle using our SOHCAHTOA and our basic trig functions. Now, as we kind of look at some applications of some of this, here's an example using a rhombus. We do know that a rhombus has this rhombus has a perimeter of 40 centimeters and an interior angle of 70 degrees. We want to know the length of the two diagonals to the nearest tenth of a centimeter. So I'm looking for the length of this diagonal, and I'll use a different color here, and the length of this diagonal. A couple of things to remember about rhombuses, rhombi, going back to geometry. The diagonals in a rhombi are always perpendicular, so we know that these are all right angles, meaning we have 4 small right triangles here. The diagonals bisect each other, meaning that if I can find one side of this blue segment, I will also know the other side. And the diagonals bisect the angles, meaning that this angle here has been cut in half, has been bisected. This angle here has also been bisected. Now, because it tells us that the perimeter is 40 centimeters, remember that in a rhombus, all of the sides are equal. That means that each side is 10 centimeters. So I can come back to my diagram and maybe label this side right down here as 10 centimeters. One of the interior angles is 70 degrees. So I'm going to go with this one right here. That angle is 70 degrees. Since it was bisected, we know that this angle on this side is 35 degrees. Obviously, this one over here is also 35 degrees. But that's enough information here to help me solve for some of the missing information that I'm looking for. If we look at just one of these triangles, I'm just going to highlight it in green and maybe redraw that triangle right down here so we have a little bit more room to be able to show this. We have this 10 centimeters here, and we have a 35-degree angle, and we need to be able to find this side in blue and this side here in red. So I'm going to go back to those trig functions. I am looking for sides. However, I cannot use Pythagorean theorem if I only know one of the 3 sides. So I do have to go back to my SOHCAHTOA and figure out which trig functions might be helpful here. Always decide which side you're going to solve for first. So I'm going to solve for this one. I'm going to call it R for the red side. And I'm going to be using my 35-degree angle that I was given. And of course, I'm going to be using the 10 because that was one of the sides that I know. So in relation to that 35-degree angle, this side here is opposite, and I've been given the hypotenuse, which means once again, I'm going to be setting up a sine equation for this one. Now in this case, I know the angle, so I'll do sine of 35 equals my opposite, which I called R, over my hypotenuse 10, and I'm going to solve this equation. Now you can solve it by cross multiplying. If you say over 1, multiply these together, that's R, and then multiply these together, the sine of 35 times 10. That right there should give me my R value. And again, if I grab the calculator, sine of 35, close my parentheses, times 10, I'm looking at a side of approximately 5.7. Now keep in mind that was half of the one diagonal. I was trying to find this full diagonal. So if I double that, multiply by 2, I'm going to get the first diagonal to be about 11.5 centimeters in length. Now I can do the same process to be able to find the other diagonal. This is going to be my side in blue. I'm going to call this B. And I'm going to use the same angle and the same hypotenuse. Keep in mind, though, that side B is adjacent to this angle, which means when I'm solving for side B, I'm going to have to use the, I just realized I missed the H here, but in using side B, I'm going to have to use the cosine function. So this time I'll do the cosine of my 35-degree angle equals the adjacent, which is B, over the hypotenuse, which is 10. Once again, to solve for B, I can cross multiply, and by cross multiplying, that allows me to multiply these two together. So I can do the cosine of my 35-degree angle times 10, and we've got cosine of 35 times 10, giving me about 8.2. Okay, now remember that this is half of that diagonal, so I'm going to need to double that to find the full diagonal. Again, you'll notice that I'm trying to use everything in my calculator, so I'm not rounding until the end. So if I multiply by 2, I get about 16.4 for the second diagonal. You'll also notice that after I found the first side of 5.7, I continued to use a trig ratio to find my second side rather than using Pythagorean theorem. And again, that just goes back to the fact that 5.7 from the first side was rounded, and we don't want to be using rounded values. Okay, so I'll talk a little bit about the angle of elevation and angle of depression. One thing to be aware of is that the angle of elevation and the angle of depression will always be equal to each other due to what we learned back in geometry again about alternate interior angles. As long as we have two parallel lines, so for example, if this line segment and this segment down here are parallel, then these angles that are formed here are alternate interior angles, and they will always be equal to each other. In terms of angle of elevation and depression, it is important to understand that the angle of elevation and depression are always the angles formed from the horizontal. Okay, for example, and that does become pretty important depending on the wording of things. So for example, looking at this picture of the building, if we have a person standing on top of the building and I give you the angle of depression, that angle of depression refers to the horizontal distance of the person kind of looking out from the top of the building, and it's the measure of the angle coming down from that horizontal distance. Now, there's a couple of things that we can do with that. If we do know this angle, let's say that this angle of depression here is 30 degrees, okay? Keeping in mind that these two angles together form a right angle, we could find this interior angle of 60 degrees as well. Because that angle of depression is going to be congruent to this alternate interior angle, we know that this is also 30 degrees. And of course, wherever the building meets the ground, that's going to be a right angle. So ultimately, we end up with having these right triangles, but we do want to pay attention to where the angles are actually given. Here's an example using some of these. So let's say we had a 75-foot flagpole casting a 43-foot shadow. So if I drew a flagpole, doesn't have to be fancy. Shadows, of course, are going to be falling on the ground. So we know the flagpole itself is 75 feet. The shadow is 43 feet. The flagpole and the ground should make a right angle. We want to find the angle of elevation from the tip of the shadow to the sun. So the tip of the shadow is right around here. We're looking at the angle of elevation, so always find your horizontal and go up. I'm looking for this angle toward the sun. Now again, we're not assuming, we know that the sun is going to have to be over here, because if the shadow is falling to the right of the flagpole, then the sun has to be on the other side of the flagpole. So we're looking for that angle right here. We can use this right triangle here to help us find that. I'm going to call this angle A. And again, we can use some of our trig functions. The 75-foot is opposite of my angle. The 43-foot is adjacent to my angle. And again, using my SOHCAHTOA, which you'll notice I'm kind of writing out each time, the one trig ratio that compares opposite and adjacent is tangent. So I'm going to do the tangent of angle A equals the opposite over the adjacent. And again, if I'm solving for an angle, I'm going to be doing the inverse of tangent. I'm sorry, the inverse tangent of 43 over 75. And inverse tangent of 43 over 75, let's see, second tangent, 43. I apologize, 75 over 43. Let's try that again. Inverse tangent, 75 divided by 43. We get about 60.2 degrees. So angle A is about 60.2 degrees for our angle of elevation. Okay, looking at a second example, we have a man climbing 213 meters up the side of a pyramid. So if he's going up the side of the pyramid, I'm going to say that one side of the pyramid is 213 meters. And he finds that the angle of depression back to his starting point is 52.6 degrees. So keep in mind, he's now at the top of the pyramid. And this down here was his starting point. So when determining my angle of depression, okay, back to his starting point, we need to think about the horizontal. Always think about the horizontal. In fact, I would recommend that you draw it in, okay? The angle of depression is the angle that he went down from that horizontal. So this angle right here is my 52.6 degrees. Now notice, guys, that that angle is actually outside the triangle. However, because we know about alternate interior angles, we know that this angle down here is also going to be 52.6 degrees. So I've given you the angle of depression, but I can use that as my interior angle as well. We want to know how high off the ground is he. Well, his height off the ground should always be measured perpendicular. So when I'm looking for his height, I'm actually looking for this perpendicular distance coming straight up from the ground, which is where, again, we have this right triangle, okay? If we use this angle as kind of our reference angle, the side we're looking for is opposite that angle. The side that we were given is the hypotenuse. And again, if we go back to our SOHCAHTOA, the trig function that compares opposite and hypotenuse is sine. So we're going to be doing the sine of our 52.6 degree angle equals our opposite h over our hypotenuse, 213. And again, if I cross multiply, then to solve for h, I will be multiplying these together. If I do sine of 52.6, close the parentheses, times 213, I'm going to get a height of about 169 says round to the hundredth, so 169.21. My units are meters, so my answer is 169.21 meters. Okay, here's another example. A cellular telephone tower that is 150 feet tall is placed on top of a mountain that is 1,200 feet above sea level. So if we start with just drawing that information, draw my mountain. Okay, the mountain itself is 1,200 feet above sea level. Keep in mind that whenever we're talking about a height or an altitude, that's always going to be a perpendicular distance. So I'm kind of going straight up the middle of the mountain. At the top of the mountain is this cell tower. And we know the tower itself is 150 feet tall. We need to know the angle of depression from the top of the cell tower to a phone user who is 5 horizontal miles away and 400 feet above sea level. So let's talk about where our cell phone user is. Okay, he's 5 miles away from, we're going to go with away from the kind of the center of the mountain. So if I kind of go 5 miles away, but he's also 400 feet above sea level. So I'm not going to start at the bottom. I'm going to go around here. Here's my cell phone user right here. Okay, I know that the distance above sea level is 400 feet. That's why I didn't start him out at the bottom. And we know that he is 5 miles away. Okay, keep in mind that everything so far has been given in terms of feet, except for this unit here. We do need to have consistent units. So the first thing you're going to want to do is convert your 5 miles into feet. Remember that there are 5,280 miles in a foot. So 5 times 5,280, it's going to be 26,400 feet. Okay, so instead of calling this 5 miles, let's relabel this as 26,400 feet. Now we're consistent units. We need to know the angle of depression from the top of the cell phone tower. So if I go to the top of the tower, and I'm going to go down to where the cell phone user is. So I'm looking for the angle of depression. Now here's where you got to be careful again. The angle of depression is from the horizontal. So if I'm asking you to find the angle of depression is this outside angle. Okay, this is what I'm actually solving for. However, I know that that angle is the same as this one, so this is the angle down here that I'm actually going to find since that's inside the triangle. So I'm going to kind of highlight my triangle here for a minute. I've got a right triangle right here. And let's think about some things that we know about this right triangle. In fact, I'm going to redraw it off to the side here a little bit. Okay, I know that we've got this right angle. I know that I'm looking for this angle right down here where the person is. I'm going to call that A. I know that, let's see here, I know that this distance, this horizontal distance is 26,400. Sorry. And then my vertical distance. Now keep in mind, vertical distance, you have 150 feet right here. You have this distance, okay, but not all the way to the bottom. We have to subtract that 400 feet where the person is actually standing above sea level. So really we're looking at 1,200 minus 400. We're looking at 800 feet. 800 feet plus the 150. So if I add these together, that's giving me 950 feet for the height of the triangle that I'm looking at. Okay? And again, I'm trying to find that angle A. So the 950 is opposite of angle A. This is the adjacent to angle A. My tangent function compares opposite and adjacent. So tangent of A equals the opposite over the adjacent. And to solve for the missing angle, I will do the inverse tangent of 950 over 26,400. Let's try that here real quick. Inverse tangent of 950 divided by 26,400. And I'm going to get an angle of about 2.06 degrees. So the angle that I'm looking for, 2.06 degrees. And keep in mind that that's the same as this angle of depression that I was looking for. So really be careful with these problems that you are paying attention to the picture itself. All of the details become important when you're actually drawing out. That kind of concludes our example. So for tonight's homework, you're going to be completing the first Math Excel assignment. It's going to have a little bit of just solving the triangle as well as some questions involving angle of elevation and angle of depression. Feet. Oops. Picture. And